this video, we'll talk a little bit more about functions and their graphs. And I tried my best to draw a function here that is going to help us identify a few features about it. So, 1. Identify intervals on which the function is increasing, decreasing, or it's constant. I want you to imagine that you are driving a car, and I'm not very good at drawing. This would be our car. Obviously, we are going up the hill, right? So we would say that our function is increasing. So we're going up the hill, we get to the top of the hill, and then the car, which, let's see, again, tough job here. The car is going downwards, so the function is going to decrease, and then it's going to increase again and decrease again. So how to identify those intervals? And be very careful, those intervals are open intervals, so we're going to use parentheses. So the function, if we look at the graph, the function is increasing here, right? So to find the interval, well, where is it increasing? Well, it's increasing on the x-axis on this part, right? The function that we have, it's actually expanding on this interval, and because we have this arrow, it goes on and on. So how do we read that interval where the function is increasing? Well, it's coming all the way from here, right? And it stops here. So that means from negative infinity to -5, and we close the parentheses. Again, open parentheses, and why do we stop at 5? Because that's where the function reaches the top. Now, next, the function is decreasing, so it's coming down here. Now, on what interval is that happening? Well, the x values where that is happening are from here to here, so the x values are from -5 to 0. So the x values when we identify intervals. After that, the function, it's increasing again. On what interval is that happening? Well, it's on this piece. So in between these two values, right, which is from 0 to 5. So the function, it's also increasing on 0 to 5. And then the function is decreasing. And where is that happening? On this interval, which is from 5 to infinity, right? The blue, I tried to color code it. The blue intervals are where the function is decreasing, and the green intervals are where the function is increasing. Okay, but taking a look at this, so we answered the first question. Taking a look at this graph, we also notice that it looks like it has hills and valleys, right? So we are expecting to see maximum and minimum. Now they're called relative because, let me show you this graph here. Right here, this would be a maximum on this region, while this would be a maximum on this region. So this would be a local maximum for our problem, or relative maximum. They are the same, they are synonyms. So in this case, let's look for maximum. So do I have maximum values? Yes, I have. This is a maximum value. This is a maximum. Maximum occurs. Now, what is that actual value? How tall is this? Well, this is 5. So the maximum is 5, and there is a maximum of 5 here as well. So the maximum is 5, attained at x equals, so where did that maximum occur? At this -5 and at this 5, right? The x values were 5 and -5, but the maximum value was just 5. Now minimum, so I can see a valley here, right? This would be the valley. So the minimum would be here. Now what is the value of that minimum? How big is this? Well, the minimum is -5, and it's attained at x equals 0. Now if we make a connection, or also let's take a look at 3. I have too many things to want to share with you. Identify if the function is even or odd. Now my graph is not that perfect, but we can see that if we would fold this graph on y-axis, we will notice that the graph would match. So the function is even because the graph is symmetric with respect to y-axis. So I wrote here a little bit of theory that should help you. If a function is even, then the graph is symmetric with respect to y-axis, and analytically we would calculate f of -x, and if it's equal to the function f of x, then the function is even. Also, this symbol here means if and only if, so it's not just implies, it goes both ways. Now if f is odd, then the graph of the function is symmetric with respect to the origin, and if we calculate f of -x, we should get negative f of x. So if that happens analytically, then the graph is odd. And I'm going to graph a few parent functions here to just practice a little bit and look at also at the domains and if the functions are even, odd, and what is going on. Okay, so I graphed here 4 functions. So let's talk about each of them. So I have f of x equals x, and I have this straight line, right? And so when we take a look at it, what can we say? Well, we can say the domain is -infinity to infinity, and the range is -infinity to infinity. Also, we notice that it's symmetric with respect to origin, which means this function f is an odd function. And if I calculate f of -x, I notice I get -x like that, which is negative f of x. So we can do that analytically as well to prove that this is an odd function. From what we've learned last time, I can also say that the x-intercept and y-intercept at the origin, and that's pretty much it. Now let's take a look at the next one. G of x equals x squared. I made the graph by giving some values. I actually gave the values -1 and 1 and 0. And what do we notice? We notice right away that the domain is from -infinity to infinity. It goes all the way, right? The range is from 0 to infinity, right? Because the graph goes only this way. There is nothing here. I can also say that the function is decreasing, right? That car is going down on which interval? On this interval, which is from -infinity to 0. And the function is increasing, so it's going upwards on which interval? On 0 to infinity. I can also say that there is a minimum value, this all the way down, of 0, and attained at x equals 0. Also, if we fold this over y-axis, it matches. So G is, you see, I wrote F, it should be G. G is even. And we can also do that mathematically. If I calculate G of -x, I get -x to the second, which is x to the second, which equals G of x. So we proved analytically that it's even as well. Okay, let's take a look at the next one. H of x equals x cubed. So I drew the graph. The graph looks like this. We give some values. And what do we notice? Well, the domain of h of x is, so it spreads all over, right? If I draw this x-axis, I can see that the graph goes all the way on that. So it's from -infinity to infinity. The range now on the y-axis, it goes all the way, right? Any value from x has a value in y, so the range. Now I can also say that the function h, it's increasing. As you can see, it's going all the way, it's increasing. So the function h, it's increasing on negative infinity. So it just starts and it just continues increasing. Also, h, it's an odd function because the graph is symmetric with respect to the origin. Just pick a number from here. If I go all the way straight to the origin and then straight away, I'm going to hit at the exact point, point on the graph of h. Or we can do h of negative x. It's negative x to the third, which is negative x to the third like this, which is equal to negative h of x, which is exactly what being odd means as a function. Okay, and let's discuss I of x, which is absolute value of x. I drew it here, is this 2. And so what can we say? Well, we can say that the domain is from negative infinity to infinity, right? It spreads all over the x-axis. The range, so the y-axis, is just this piece, right? There is nothing here that it's my graph. The graph is just those two arms. So it's from 0 to infinity. Also, the function I is decreasing, right? It's going downwards. So the function I is decreasing on, well, where is it decreasing? This decreases on this part of x-axis. So on negative infinity, 0. And the I, it's increasing, so then it starts going upwards, right, on this piece. So on 0 infinity. The intervals where the function increases and decreases are the x-axis. So we just look what happens on the x-axis. What else? This function, if we fold it over y-axis, it's gonna overlap. So what does that mean? It means I is even, or we can do I of negative x equals absolute value of negative x, which is absolute value of x, so it's equal to I of x. So I is an even function. Now, these functions that I wrote here, where we have more than one expression for the function, are called piecewise functions. So this function says, if your x values are more than or equal to 6, you should use x minus 5. If your values that you choose are less than 6, you should use 2x. So let's see how or what we can do with this function. So I'm going to graph it. To graph it, I'm going to make a table of values and put x and f of x. And then we always put the value that it's breaking up our function, or values, because we can have even more than just one. So in our case, it's 6. And I'm going to put a bar here. And I'm going to calculate the value of the function to the left of 6, which means for less values than 6, and for greater than values than 6. And now I'm going to pick two numbers to the left of 6, 5 and 4, and 2 to the right, 7 and 8. So f of 4. Now f of 4 is less than 6, so I'm going to use this expression, 2 times 4, 8. F of 5, it's again less than 6, so I'm still going to use the second one, so it's 2 times 5, which is 10. F of 6, well, f of 6 can be calculated with this one because that's where it's included. But I'm going to calculate this with this value as well, which is going to give me 2 times 6, 12. But I'm going to put it here, 12. And I'm going to mention that it's an open dot when I'm going to make my graph. And now let's do the other ones as well. F of 6 with this line is going to be 6 minus 5, which is 1. And, here with closed dot. And let's calculate f of 7 and 8. So now that we have this table of values, let's graph them. So 4, 8. 5, 10. 6, 12. And at 12, it's an open dot. So I'm going to make sure I put open dot here. And this graph is going to go like this. And it's probably going to pass through the origin. Now, at 6, 1, close dot. At 7, 2. And at 8, 3. And this would go this way. And this is a function. And is the graph of a piecewise function. I hope this helps.